In this minimization problem, we start by rewriting the inequality constraints in order for them to fit the generic setup for a nonlinear optimization problem. The picture to the right shows the feasible region, shaded in blue. I have also computed the gradients of all of the constraints in order to verify that they are linearly independent, as the Kuhn-Tucker first-order conditions only apply to regular points. Those are basically the points where the gradients of the active inequality constraints are linearly independent. Also, on the right-hand side, I've written the first-order necessary conditions that candidates for minimizers must satisfy. In particular, the complementary slackness condition that I will show at the very end for the potential candidates that we do find. So let's go case by case, starting by ignoring the constraints entirely and pretending it's an unconstrained problem, in which case we try to minimize f by first setting its gradient equal to 0, as we would usually proceed, but that gives a contradiction, which is kind of expected since f is really a plane, and an unconstrained minimization for a plane would not have any solution, nor really make any sense. So now let's consider what would happen if we imposed constraints. In particular, let's take G2 to be active, so the candidate lies along the circle to the right. And if that's the case, then we need mu1, the first Lagrange multiplier, to be 0 so that the complementary slackness condition is satisfied. So let's just go ahead and compute this first order condition using the gradients that we computed above. Keep in mind that we also have to satisfy the equation of the circle itself. And if you actually carry out the calculation and solve the system, you get the following solution, which, keep in mind, is not necessarily a minimizer just because it passes the first order condition. It's simply a candidate for a minimizer. Let's also just keep track of our Lagrange multiplier, as we're going to need that later. Now let's consider being constrained along the circle that's centered at the origin. So the Lagrange multiplier for the second constraint must be 0, so it doesn't appear. So the idea is just as before. I'm going to set up my system of equations using the gradients of the active constraints, in particular just the one. So just bear with me as I write them out. And now hopefully you notice that if you look across the first row, you will see that the equation actually gives a contradiction, because as I need the Lagrange multiplier to be strictly positive, this would imply that x is strictly negative, which we cannot have because we have to satisfy the third constraint in the back of our minds. The third constraint, of course, says that x cannot be negative. So the simple conclusion is that there are no candidates for minimizers along this constrained region. So far, we've only really found the one candidate for a minimizer. There's only really one case left for us to check, and that is when both constraints are active. In other words, our candidate is expected to be along both circles at the same time, which really just gives the two possible points at the intersections. And we don't have to do anything too complicated here. I've written down the points where the two circles intersect. They're not too difficult to find. And now I'm claiming that these 2 points of intersection are actually candidates for the minimizers, and in particular they should satisfy the first order necessary conditions. That is what I've written up above in the box. However, notice now that if you know the points, you have a system of 2 linear equations in terms of the Lagrange multipliers, and if you do solve this system, you end up getting that mu1 is negative, contradicting our assumption that they must both be positive. And finally, I want to show you what happens when we take G3 to be active. In other words, x itself must be 0. Well, if that's the case, then you're really just looking at the origin, and so that's your only possible candidate. If you're at the origin, then the gradient of the second constraint, the second circle to the right, which is actually active as a result, is going to be itself linearly dependent with the gradient of your currently active constraint. And so it ends up that since they're not linearly independent, that this point cannot be regular. And if it isn't regular, it does not satisfy the first order Kuhn-Tucker conditions. And so finally, the only candidate, after having gone through all of these cases, is the following, which results when we take G2 to be active. And so now, the very last thing we still have to check is the complementary slackness condition. That is, I just want to make sure that G2 evaluated at this candidate comes out to be 0. So let's go ahead and plug in the candidate that we found. And if you do this math, you will get the following. So that is root 5 minus 1 over root 5, subtract 1, whole thing squared, and then that squared. And hopefully you can see that this whole expression comes out to equal 0. And finally, the very last thing is to notice that mu2 itself is positive, and their product is precisely 0.